Hi class, and welcome to your second mini lecture, this time on Newton's laws and his theory of gravity. Remember, these lectures are intended to be listened to after you've done the associated reading. Newton comes toward the end of the Copernican revolution, and he provides some very important laws concerning the motion of objects. So he's got 3 laws of motion and then his theory of gravity. And these laws are very important because they now give physical reasons for why objects move as they do, including the planets. Kepler's laws stated what the planets do. He talked about what the shapes their orbits have. He had the equal area and equal times law. He knew how long their periods should be with respect to how far away they are from the sun, but he didn't have any physical explanation for why the planets behaved as they did. And so that's where Newton's laws come in. Newton's first law is known as the law of inertia, and it states that an object at rest will remain at rest, and an object moving in a straight line at constant speed will not change its motion unless an external force acts on it. Alright, so a lot of people paraphrase this: objects at rest remain at rest, objects in motion remain in motion, unless, an outside force acts on it. Certainly I experience the law of inertia on the weekends when I'm sitting on my couch. I certainly want to remain at rest on my couch, but that's not exactly what he was talking about. Here are some examples of Newton's first law. So, rockets in space, if they've been launched up and have some sort of velocity going, you can turn off their engines and they will continue to coast in a straight line at constant speed. Formally, yes, there's a little bit of force acting on them, force of gravity, but it's very small, and so that initial momentum that the rocket has will remain with it, and it'll just remain at constant speed. A little more everyday example, a hockey puck gliding across the ice. It will remain at constant speed more or less until it hits something. An ice rink is a very close approximation to a no-friction environment. If there were absolutely no friction, then that hockey puck would continue on at exactly the same speed forever or until it hits something. Another example of Newton's first law, which may not seem as obvious, is that if you're riding in a car and you toss something up, it will land back in your hand. And if you think about that, that's sort of interesting because you tossed it from your perspective, from your perspective straight up. But if you think about the motion of you and the car, you're moving forward, and yet the item still fell into your hand. So it too must have moved forward, and that is actually a result of inertia. If you're holding, say, that coin in your hand, it has an initial velocity, the velocity of you in the car, and it will keep that velocity as it travels through the air and comes back down. So those are all examples of Newton's first law of inertia. Newton's second law has to do with force and acceleration. So it says, when a force is exerted on an object, its acceleration is inversely proportional to its mass. So in terms of an equation, we see that acceleration is equal to force divided by mass. More commonly, you will see this written as F equals ma, or force equals mass times acceleration. So let's think of an example of that. You may recall there being a bully on the playground when you were young, and let's say that bully goes up to someone, they're going to pick on someone larger than them, and they push them with some force. Well, if that person is massive, meaning heavy, they aren't going to accelerate much. That push isn't going to make them fall down. That's not going to make them move very much. Now, the bully may not be very satisfied with that, so instead, he or she's going to go pick on someone smaller than them. They can still apply the same force, so they go to shove them with that same force, but now the person that they're picking on is less massive, less heavy. and so they accelerate more, right? That person might stumble backwards or might fall down. So as the mass of the thing you're pushing increases, the amount you're able to accelerate it decreases, and that probably makes some intuitive sense. Newton's third law says that when object A exerts a force on object B exerts an equal and opposite force on object A. Sometimes this is commonly paraphrased as for every action there is an equal and opposite reaction. All right, just standing on the floor, you experience this. All right, as you stand on the ground, you are exerting a force on Earth. And if Earth was not exerting a force back on you, you would fall to the center of the Earth. Okay, but there's a support force there, and it's equal and opposite to the force that you are exerting on the ground. Now let's take another example, collisions. All right, sometimes things collide that are of very different masses. For example, a bug and your windshield. And in that case, you might ask, well, who's having the worst day? Well, clearly the bug is having the worst day, right? The bug gets squished and dies. But in terms of Newton's third law, the windshield and the bug experienced the exact same force. It was equal and opposite when they collided. So then why is the bug having the worst day? Well, that actually comes back to Newton's second law. So the difference here, although the force applied was the same, the mass of the car and the mass of the bug are very different. And clearly the mass of the bug is much less. So the bug experiences a much larger acceleration and therefore gets squished. So that wraps up Newton's three laws of motion, and now we're going to move on to his theory of gravity, which says that for any two objects that have mass, there will be a gravitational force between them. And that gravitational force is proportional to the product of their masses, so the mass of the first object times the mass of the second object, divided by the square of the distance between them. So divided by the distance times itself. So you can see that equation right here. F is equal to G times M1 times M2 divided by R squared. M1 is the mass of the first object, M2 is the mass of the second object, and R is the distance between them. Now G, that constant in the numerator, was found empirically, meaning through experiments. I will show you what it is, but you're not really going to need to use it for any calculations. So let's look or think back to this theory of gravity. It says for any two objects with mass, this gravitational force exists. So that means that as you are sitting in your room right now, everything in that room is gravitationally attracted to you, and you are gravitationally attracted to it. So then why are these items not flying towards you the way that you fly toward the earth if you try to jump away from it? Well, it comes down to the overall size of that gravitational attraction. Per unit mass, it's very small, and since you are not very massive and the items in your room are not very massive, the force between you is just very small. It's different when we're talking about your gravitational attraction to the earth. Earth is extremely massive, 10 to the 24 kilograms. So the gravitational force, although per unit mass is small, when you're talking about something as large as the earth, it makes a big difference. So that overall size is reflected in the value for G. And you'll see that it's small, on the order of 10 to the negative 11. So we'll get back to that in a little while. All right, the next thing I want to draw your attention to is this graph right here. All right, what it is showing is force as a function of distance. And so what it's showing is the squared relationship. Force goes down by the distance between the two objects squared. So as the two objects get further and further away from one another, the gravitational force goes down, but not linearly, right? It's a squared relationship there in the bottom. And so you get this type of shape on the graph. If you double the distance between the objects, so you go from a distance of 1 to a distance of 2, the gravitational attraction between them goes down to a quarter of what it was initially. All right, so it's exponential, okay? Down on this edge, I drew this a little sloppy, but the original graph doesn't actually touch the axis. It approaches an asymptote, which is to say that it gets closer and closer to the axis but never touches it. So what does that mean? Well, basically that means that no matter how far away two objects are, there will be some gravitational force between them. It'll be very, very, very small, but it will never go to zero. So for example, we launched Voyager 1 and Voyager 2 in 1977. They have now moved out beyond our solar system, so they're very, very far away. And yet there is still a small tug, a gravitational tug, for them to come back to Earth. They're never going to. Their speed is large enough that they have escaped our gravitational pull, but that doesn't mean the gravitational pull has gone down to zero. Now let's take a look at a few multiple choice questions that will help you start thinking about the implications of gravity. All right, so this first one says, which of the following correctly describes how the gravitational force exerted by asteroid A on its partner asteroid compares to the gravitational force exerted by asteroid B on its partner asteroid? Alright, so I'm going to actually kind of talk you through this first one, and then the next one I'll have you do a little bit more on your own. So first things first, we're looking at the gravitational force exerted by A on its partner and by B on its partner. When we first tackle this question, we might start by looking at asteroids A and B and considering what force they might exert on their partner. And we notice that asteroid A has a mass of 5 in some arbitrary units, and B has a mass of 3. So we might think at first, oh, well, A is more massive, therefore it would exert a larger gravitational force. But we need to be careful. The gravitational force exerted by an object does not depend solely on the mass of just that object. The gravitational force depends on the product of the masses of the two objects involved. Remember Newton's third law. For every force there is an equal and opposite force. So whatever gravitational force A is exerting on its partner is also exerting back on A. So what we need to do is calculate the gravitational force between A and its partner, and then separately between B and its partner, and compare the two. So let's get started. So remember, F goes like the product of the masses divided by the distance squared. We're using arbitrary units here. We're not going to worry about all that, so we're not going to involve the gravitational constant g. So for A and its partner, we've got F is proportional to 5 times 3 divided by 1 squared. All right, so that means the gravitational force for A in some arbitrary units is 15. So now let's look for B. The gravitational force there is proportional to 3 times 5 divided by 1 squared. So take a minute to consider the answer to this question. So the answer to this question would be C. The force of A on its partner is equal to the force of B on its partner, and that is because the product of the masses involved are the same in each case. For A, we've got a mass of 5 times a mass of 3. For B, we've got a mass of 3 times a mass of 5. Those both come out to 15. They are at equal distances of 1, and so the overall force calculated between the asteroid and its partner is the same. Now take a look at this one using the same sort of reasoning, but now not only are you going to have to think about gravity, You're also going to need to think about Newton's second law, force equals mass times acceleration, because in this one we're looking at the acceleration experienced by asteroids A and B. So I'll give you a moment to read this and think about the answer. Go ahead and hit pause so that you don't reveal the answer before you're ready. If you're ready for the answer, I'm going to move on. If not, go ahead and make sure this is paused. Alright, so the answer to this question is that the acceleration for A would be equal to the acceleration for asteroid B. Alright, so let's talk about how that is. Well, first of all, we have to find the gravitational force between them, because acceleration depends on force and mass. So again, we're going to look at the product of the masses divided by the distance squared. So we're going to have, for A and its partner, we're going to have 5 times 3 over 1 squared is 15. And for B, we're going to have 5 times 5 divided by 1 squared is 25. Alright, so that is the force. That is the force between A and its partner and B and its partner. They're equal and opposite forces. But the way the different asteroids experience that force is different because the acceleration is dependent on their mass. So we have to calculate the acceleration for A, asteroid A that is, as being F over m. So that's 15 divided by the mass of A, which is 3. So it's an acceleration of magnitude 5 in some arbitrary units. For asteroid B, we've got acceleration is equal to F over m. The force experienced by B and its partner was 25 divided by the mass of asteroid B, which was 5. So that means the acceleration for asteroid B is also of magnitude 5. Again, of some arbitrary units, since we're not bothering with the gravitational constant and units of kilograms and meters, etc. for the asteroids. Okay, let's keep trying some others. Okay, this question I'm going to let you read to yourself and attempt to answer before I discuss the answer. This one is getting more at the distance dependence on the gravity equation. If you're not quite ready to hear the answer, go ahead and pause this. Otherwise, we're moving on. This picture shows the Earth-Moon system not to scale and 3 possible positions for a spacecraft traveling from Earth to the Moon. Note that position B is exactly halfway between the Earth and the Moon. What would the spacecraft do next if it were coasting toward the Moon at position A? So we have a spacecraft out here in the center, and if I go ahead and just draw some sort of craft, it has mass, okay? So there's going to be a gravitational attraction between the spacecraft and the Moon, and there will be another gravitational attraction between the Earth and the spacecraft, okay? And that force is going to cause acceleration. Now the mass of the Moon is much less than the mass of the Earth, okay? So the gravitational force between the Moon and the spacecraft, which depends on the product of their two masses and the distance between them squared, is going to be less than the gravitational force between the spacecraft and Earth. The mass of the Moon is much less, so the product of the Moon times the spacecraft is less, and the distance is equal, right, at position B. So right at position B, the distances would be the same on either side. And so the mass of the Earth being larger would create a much larger gravitational force. So now we've got a gravitational force and it's going to cause acceleration. All right. In the center, the gravitational acceleration, the gravitational force between the spacecraft and Earth is larger. Okay, if I move it to A instead of it being at B, that reduces the distance between the spacecraft and the Earth. So what's going to happen to the gravitational force between them? Well, it's going to go up, right? If the distance is reduced, the gravitational attraction between them goes up. So the force is going up. If the force goes up, acceleration goes up. All right, the object causing the acceleration is Earth. So the direction of the acceleration is going to be back toward Earth. All right, so if the spacecraft is coasting, law of inertia, right? So it's just coasting toward the moon, but there's a gravitational attraction pulling it back toward Earth. What is it going to be doing? It's going to be slowing it down. All right, it will continue to move toward the moon, but it will be slowing down. Now we've done a couple of comparisons of gravitational force by just using the proportionality of the force being dependent on the product of the two masses and the distance between them squared. But just to show you the value for g in the full equation, again, this is called the gravitational constant. It was found experimentally, and the value is 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. So it's that times 10 to the negative 11 that really makes the value very small and gives you a sense for why we don't have strong gravitational interactions with everyday objects on Earth. Gravity is responsible for the motion of projectiles on the surface of Earth, so anything that we throw, launch, lob, etc., as soon as it has been ejected from our hand or launched as a rocket or whatever the case may be, so long as it's no longer being propelled, it's under the influence of gravity and will behave in a particular way. It will behave as a projectile, and it will either go straight up and straight down if it was not given any sideways velocity, but if it had both up velocity and sideways velocity, as most balls would, for example, baseballs, footballs, etc., it's going to have this characteristic parabolic path. Again, this is what we would call the path of a projectile. It's under the influence of gravity, which is always directed toward the center of the Earth, so no matter which way you launch it, it will be accelerating downward. So let's look at some various quantities for a projectile as it moves through space. Okay, so what I've got here is a projectile showing that characteristic parabolic path. And then we've got 3 vectors shown for each position. Vectors are arrows that stand in for a quantity. So for example, velocity is represented by a red arrow. The length of the arrow gives you a sense for how high the velocity or the speed is, and the direction of the arrow gives you the direction of its travel. So for example, in this very first position, the velocity arrow is long and pointing up, so we know the ball at that point has a rather fast velocity and it's moving upward. The other 2 vectors shown are the acceleration and the force vectors. The acceleration in purple, the force in black, and they are both pointing down throughout the flight of the projectile, and they remain the same length. So what that says is that they are constant throughout the flight. Gravitational acceleration on the surface of Earth is constant at about 9.8 meters per second squared. You don't need to really know that value, but you do need to know that acceleration is constant. Acceleration is simply a change in velocity. Alright, so position 1, velocity is high, it's traveling fast, and the velocity is up. If you look at the second position, the velocity has slowed a bit, All right, the arrow is not as long, but it's still indicating that the ball will continue to travel upward. At the top here, there is no velocity vector. All right, what that indicates to us is that the ball, for a brief second, is experiencing a velocity of 0. It slows to nothing. And then at that point, it will start to be dragged back down to Earth, and its velocity will increase in the downward direction as it makes its way back toward Earth. So the acceleration, always pointing downward, is indicating that tug from Earth to come back down, and it is constantly slowing the ball down as it makes its way up its path. All right, when it gets to the very top, that acceleration vector pointing downward has canceled out all of the upward velocity and is going to start bringing it back down. Notice that, however, there is no velocity vector here, there is an acceleration vector. So the ball is always experiencing acceleration. The acceleration is back down toward the surface of Earth. If at the top acceleration didn't exist, then the ball would just hover there. So keep that in mind. Acceleration is always present. It's always in the direction down toward Earth, and it's due to the gravitational force. So we've been talking about the theory of gravity and how gravity always pulls projectiles back down to the surface of the Earth. But we have been able to launch things off the surface of the Earth and have them travel throughout the solar system. So we know it is possible to overcome that gravitational field. So how is that achieved? Well, we have to launch the object with greater than what we call the escape speed for Earth. And this is the speed, again, necessary for a projectile to completely escape Earth's gravitational field. So to think about where this idea came from, we can do sort of a thought experiment. So imagine yourself on a really tall building and you're throwing a baseball. Okay, if you are at the top of the building and you throw the ball with just a little bit of velocity, it's going to fall pretty much straight down. If you give it a little more, it's going to go out a little more and then fall down. And then if you imagine giving it an even larger throw, it'll go a little further and then come back down to the surface of Earth. But if you could imagine throwing it hard enough, you could actually throw it so that as the gravitational pull pulls it back down, it's already gone far enough to the side that as it pulls down around the surface of the Earth. And that would essentially launch the thing into orbit. And if you threw it with even more speed, you could have it just escape the gravitational field altogether. So the escape speed for Earth is about 11,100 meters per second, or about 25,000 miles per hour. It's extremely fast. Anything less than that, the projectile will be gravitationally pulled back down to the surface or will stay in orbit. All right, so that's it for our mini lecture on Newton's laws and theory of gravity. Until next time.